Hello guys, my name is Adrian and welcome to my channel. If you are new to the channel, I'm trying here to create a small framework in order to be used for some game that I'm developing live on stream. So far I have my square that can be moved from left to right, and we have for sure translation, scaling, but for our matrix transformations we are missing the rotation. So in this video I will try to implement for my framework I will try to implement the Quaternions. Quaternions is a new structure that we have in order to represent the rotation. So far, we had the vector, which helped us to represent, for example, a position. We had the matrices, which help us to store the position, the rotation, and the scaling for an object. And now we have this quaternion, which will help us to store the orientation, rotation, how you want to call it. So I will start this video by adding two new files. I will name this Quaternion, or if you want, we can keep it short with Quat. Okay, because we have also vec, Quat, mat. So we'll keep this. Okay, first, of course, we need to make it available for our CMake compiler. And after that, we'll use the namespace mat. Okay, the same applies for the header. And what I will want to do, I will add the Quaternion, I don't know, somewhere around here in my precompiled header. How this Quaternion structure looks. First, of course, let's make it a structure in order to be similar with the other mat structures that we have. And what I would like to do, I will take the vec3, the vector with 3 elements, and I will put it on side as an example, because these are kind of similar in the, let's say, in the representation. Okay, so how we will do this? First, for a quaternion, we have something similar with columns. We have 4 elements. Okay, so the only difference is that for our quaternion we start with the W. Okay, you can start with the X, but mostly on all the tutorial libraries for the quaternions, for the mathematical part, you will see the W as the first element and sometimes initialized with 1. Okay, so we have W, I, and Z. Okay, these will be, let's say, public members. What we have for this, similar to what we have in the vectors, we'll have some length. Okay, length function. Okay, this should return a float, similar to what we have for the vectors. We'll have also a squared length. Okay, after that the normalization, of course, and what I want, okay, we can put this here in order to kind of keep the same structure with the vector. What we'll have also here, the implementation for the normalized length, squared length, it's similar with what we have in the vectors. Now the part is that if you want, for example, to calculate the rotation, okay, let's first create a function. So we'll have rotation. We'll take a vec3 to represent the axis for the rotations, and we'll have a float radians, which should represent the angle. Okay, so what is happens here? We have 4 members that can hold some orientation, some rotation, how you want to name it. Okay, we will have these functions to affect these members, but the whole idea is like this. We know in the GPU world that, and especially in OpenGL, we know that in order to move an object or to set it in the 3D world, we need to multiply it, or we need to multiply the vertices with some matrix. Of course, like I said, the matrix has position, scale, orientation, and so on. In our case, in our framework, we don't use the rotation or the orientation. with the matrices. We will use this quaternion. So what we will need, because the GPU needs a matrix, but we will have this quaternion. The GPU doesn't know what a quaternion is. So what we will need to do, of course, there is something that already exists on wiki and whatever place you want to search for it, but there is a let's say mathematical representation to have a quaternion to be, let's say, cast or converted to a matrix. So another function that we need is to call it a matrix. Okay, we will return a new matrix. So it's not, we will not store the matrix in this quaternion, but every time we want to multiply the rotation or the orientation with an existing let's say matrix for the model, for the object, we will need to convert it. We need to convert the quaternion to a matrix. So I think this is it what we need to implement for today. So let's try to, let's say, generate these functions. Okay, that's very simple. So we will start with the rotation. Why not? Like I said, these will have some axis. Okay, you choose on which axis to, let's say, to rotate. Okay, and the angle that you want. Like I said, the angle needs to be with radians. Why not degrees? Because in general with, let's say, angles, the radians are better. Like when we are referring to the radians, we are talking about P and all that stuff around the circles, mathematics. So how do we start? First, what we need to do is to have a half angle, okay? I will call it just hash A, okay? What hash A? Because in the math also I use, let's say, where it was here, I use some acronyms, some small letters to represent something. So I will keep the same here. So we have the hash A, which means the half angle, or if we want, and do you think that it will be more precise or much easier to understand, I will keep it with half angle. Okay. After that, we will need to have a sin for the half angle. Okay. So, like I said, this needs to be radians, very important. And after that, we'll use to have a sin on this angle. What we are doing with that thing? It's very simple. Now, the rotation, in order to affect the x, needs to be equal with the axis x multiplied by the sin half angle. Okay? The same we are doing for the I and Z. The only difference is that for the W, we are using a cos, okay, a cos function for the half angle. This is the only difference. And by doing this, let's also make this constant. By doing this, what we are getting, it's the, let's say, the rotation, the orientation that will be mapped on these members. Okay, this is not similar with what you have, for example, in Unity when you see X, Y, Z, and you see 90 degrees there and all that stuff. That's different. The representation of the angles will be different in this. You don't need to expect things like 90 degrees, 45, and all that stuff. It's very important to know this, okay? So this thing for the X, it will be, let's say, hard to understand in terms of the degrees, okay? If you are taking a quaternion, after we'll kind of do some rotation, you will kind of, it will be hard for you to see, okay, in X I see 1 point something value. So it means that these are somewhere like some number of degrees. Of course, we have a function which help us to convert, let's say, degrees in radians and radians in degrees. But if you don't know this, let's say, computation, it will be much harder for you to understand at the first sight what the value in X, Y, Z it is for the for the quaternions, of course, in the degree. So this is kind of the simple mathematics for, let's say, for a rotation with the quaternions. I don't have an example here for the matrix rotation, but I can tell you that it's much harder to do. And from what I remember, for each axis you need to do multiple scene computation and so on. So for this it's much easier. On the length side, like I said, it will be very easy. Return the square root for the squared length, and the squared length, it's similar with what we had for the vectors. So we multiplied with each element, we multiplied with itself, and we are adding to the final value. Okay, let's put, in order to just be, let's say, as all of the other frameworks, we'll put the W first. Of course, it doesn't matter because here we have addition and multiplication. We know this can change places, but just to kind of be more, let's say, as other frameworks. So in here, we'll have a constant auto L, which comes from length. And what we are doing, we are checking if the length is bigger than epsilon, of course. Epsilon, a very small number, a very small value. We are doing that. After that, it's very simple. We are taking each element and we are multiplying it with the inverse. Okay. Why we are doing this? Because it's much faster to kind of apply the multiplication here. Okie dokie. So let's do this for the other ones. Okay. Like I said, it's very similar with what we have here for the vector with the 3 elements. Okay. And the other, let's say, hard part is to convert this to a matrix. So what we will do, we'll have a map for first, we'll call it matrix, very intuitive. And what, of course, at the end we need to return this. And what we will do is not something like always. When I'm doing something on the math side especially, it's not something that I design or, let's say, I kind of invent. The math part is already there, and I'm not that good enough to kind of innovate in the math area. So what we need to do, we will have some constants, auto, and first we will start with the wx, which will mean that we need to multiply w with x. Okay, this is the first one. We'll have something for the w and I, and the same for w and z. After that, what we need to do, we need to do something for the x, the same xy, and the same for the z, xz. Why we are doing this upfront? Because we will kind of use these multiplications many times for each element from the matrix. Okay, so it's kind of like a cache system. You can think of it like we pre-compute these values and we are good to go afterwards. Okay, we don't need to, like, every time to do this. We can just apply xx and we know what it will do. Okay, after that, let's do one for the I. We are doing something for the I and z. We are not doing anything for the I and x because we already have the value here. Okay, and at the end, what remains for us is to do something for the z and z. I remind you that the order for my matrix, it's column based. Okay, so what we are doing, we are starting with the first matrix. Okay, column 0x equal with 1.0f minus y plus zz. Okay, I will try not to kind of explain this, to pronounce this, because it's kind of y is easy. I don't want to do it. So for the second element, of of course, what we are missing here, we need to have a multiplication like this, and the same we are doing for each element. So this will be kind of the base. Okay, just checking. So for the next one, we need to have the xz and wy. Okay, and very important, because I changed the math for to not have anything initialized in the column by default, we will need to specify the w, just a second, 0, w as 0, just that. Okay, because otherwise we will get like very ugly values here, and it will complicate everything. Okay, now what we need to do? We need to do for the second column. So we will start with the xy plus wz. I will let the AI to autocomplete if it's okay. So we have 1 minus 2.0 xx and zz, that's okay. Okay, we have very important. Okay, that's good. Nope, that's not good. This needs to be plus. Very important to be. If you are missing here, like also here, I think it's not okay. Okay, it's plus plus. Okay, that's good. We fix it. So it's very important to kind of be aware of what you are putting here. And the last one is 0. Okay, I will align things behind the scenes, or not. I'll do it now. Okie dokie. Let's do the same for the other ones. Okay. Okay, and for the last column, we are just putting the default one. And of course, the last element needs to be 1, because this is kind of the diagonal. So in order to keep some scale there, we need to put it. So that's why also we are putting here 1, okay, because we are going on the diagonal of the matrix, okay, and it needs to be initialized with 1. So that's why we have 1 minus 2, blah, blah, blah. Okay, we don't have scaling for this matrix that we are creating, so that's why we are putting 1, and we are kind of take it as the identity matrix. Okay, just let me check again the last member. So we have y and z, x, y, w, z. Okay, a minus plus. Okay, okay, we have plus minus 1. Okay, 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 and okay. Good. So this is what we need to do for our quaternions. Now, what I would like to do, I would like to kind of, let's say, try to make a use of this Quaternion class. So, just a second, let's try to build it. It built successfully. Okay, so what I will want to do, I will have here a Quaternion, sorry, math Quaternion. Okay, let's have a rotation. Okay, and what I want to do, I want to do some rotation. Let's see on the this one, this axis, okay, on the Z. And for my time, I will have like core platform time elapsed. Okay, I will, I don't know, multiply with 2.0, doesn't matter. And at the end, I will have something like, let's see if I can use it directly like this. Okay, I cannot. So what I need to do is like to have a math for here, rotation matrix. Okay, I'm not having this. So it's equal with the rotation quaternion matrix. Okay. And we are using this here. Sorry. And just let's give it a spin to see if our object is moving. So as you can see, now we have rotation. If we want to implement also the translation for this matrix, we will need afterwards to have the rotation matrix multiplied with the translation, with some matrix that holds the translations and the scale. By the way, it's very important to have the translation, after that the rotation, and in the end, if the scale is different, to also apply the scale to this one. Okay, Quaternion also resolves some things regarding the row orientations and angles and so on, but if you are more interested in this, you can search for more information on the internet. The source there is much, let's say, richer than what I can provide. But the important thing it was to have in my framework the rotation. I can now rotate things very easily. I will use this Quaternion and this rotation in order to make a small demo, which I will try to make also a video with. And yeah, that's it for today. We implemented the Quaternions. We finished with the matrix improvements, with the math improvements that we want for this framework. We have the vectors, we have the matrices, we have the Quaternions, we have the column multiplication using the SIMD. Okay, those are very fast instructions, and I think this is it. Now we need to find another part in our framework journey. Probably the next thing that we will do and we will explore, it will be to load a 3D model. For sure, an OBJ model, because it's a very easy format to do. And I think, yeah, this is it for today. Thanks for watching. Have a nice day and see you next time. Bye bye.